video, we will learn how to determine what the limiting reactant is, conceptually as well as mathematically. So we have learned so far that those stoichiometric coefficients tell us the proportions in which things react. They do not tell us how much we actually have in our system. And so, for instance, this chemical equation tells us that for every one methane molecule, we will need 2 oxygen molecules. And so one reaction will involve 1 methane and 2 oxygens. We will have, if we start with 3 oxygens, then we will have excess oxygen. And that excess stays around even as the reaction, after the reaction has finished. And so we have some terminology to help explain what we have and what we don't have. And so we have excess oxygen from the previous problem. So that's called our excess reactant. How much product we make is limited by the methane. And so in this case, our methane is our limiting reactant. Methane is completely used up. Once methane is completely used up, then we cannot make any more product. And so then the reaction would stop. Here's a different box. Same equation, same chemical equation, but different amounts of starting material. Go ahead and pause the video and try to determine what the limiting reactant is in this case. Okay, you think you have an answer? Let's talk about it. So we need 1 methane for every 2 oxygens. So I'm going to circle 1 methane and 2 oxygens. 1 methane and 2 oxygens. And so we have excess methane. We are limited by our O2. CO2 and H2O are both products. If you're trying to pick out the limiting reactant, you have to stay on the reactant side of the equation. So you have to pick out a reactant. Never pick one of the products because it's asking for a limiting reactant. That's what the question's asking for. Well, okay. There are mathematical approaches to determining the limiting reactant as well. We will cover 3 different mathematical approaches, and you just have to pick out one approach that makes sense to you. And if you learn multiple methods, then you'll be able to pick out which method will lead you to the answer more quickly. I use a combination of the first 2 methods, depending on what the question's asking for. So in our first mathematical approach, which is similar to what is shown in the textbook for the course, the strategy here is to determine the maximum amount of product that can be made. And so the maximum amount of product that can be made will be you would pick the smaller of the 2 amounts. And so if we look at this, it says how many moles of water can we make from 6 moles of hydrogen gas and 4 moles of oxygen gas. And so what you would do is you would determine the amount of water from each of those amounts. And so we are given amounts given amounts of both reactants, how much product can you make? And so we would use the stoichiometric coefficients, and this tells us that if we use up all 6 moles of H2 gas, we will make 6 moles of water. On the other hand, if all moles of O2 was used up, we would end up with 8 moles of H2O. Now that we have our math, it's time to decide which number makes sense. And so once we run out of our limiting reactant, the reaction will stop. And so once we have reached 6 moles of H2O, the reaction stops because all H2O is used up. We are unable to make 8 moles of H2O because the reaction is going to stop once it reaches 6 moles of H2O. And so it's impossible because the reaction will stop after 6 moles are made. And so the limiting reactant must be H2. And we will make 6 moles of water. And so the answer to the question, when it's how many moles of water, would be 6 moles of water can be made. Okay, so next up, it's the same problem, but we're going to be solving it a different way. In this method, we're going to be determining how much of the other reactant is needed, and then comparing how much we have to how much we would need. So it's the same question as before. And so we know that we have 6 moles of H2 and we have 4 moles of O2. We can use how much we have of one substance to calculate how much we need of the other substance. And so needed values are calculated. Calculate need. Then you compare have to need. Have versus need. You can compare that by subtracting. And so if you have 4 moles of O2 and you subtract out the 3.00 moles that you need, then you will have 1.00 moles of O2 left over. And so since we have leftover O2, then oxygen is the excess reactant, and hydrogen must be our limiting reactant. So I'm going to use that symbol for therefore is limiting. You also want to make sure that you're comparing the same substance. And then after you figure out what is limiting, then you can go back and answer the original question. All of the quantities in a chemical reaction depend on how much of the limiting reactant we have. And so we have to use that quantity of the limiting reactant to calculate all other quantities needed or asked for. And so we have our 6 moles of H2 and that we know is the limiting reactant. And so how much water we make is going to depend on that amount of hydrogen that we had to start with. So we need to calculate our moles of H2O from our moles of hydrogen. So that's when we look at the coefficients. And there's a 2 coefficient in each place. And so 6 times 2 divided by 6 is 6 moles of H2O. The last method is to figure out how many reactions could occur. And you'll know that the reaction will stop with the lesser amount of reactions. So this question reads, how many moles of water can we make from 6 moles of hydrogen and 4 moles of oxygen? So this is the same problem as before, solved a different way. And so to solve this problem, we're going to assume all H2 is used up. If all H2 is used up, how many reactions could we do out of that many moles of H2? Well, from the balanced chemical equation, that we can tell that for one reaction, we will need 2 moles of hydrogen. And so that tells us that we could do 3 reactions to use up all of our H2. On the other hand, we have enough O2 to do 4 reactions. We can't do the 4th reaction because we will run out of hydrogen after only 3 reactions. So H2 will run out after 3 reactions. Can't do 4th reaction. All right, now that you know that H2 is limiting, then you can use this amount of hydrogen to calculate how much water you need. And so we know that the amount of water we make is going to be dependent on how much of the limiting reactant we had. And so we need to cancel out our moles of the limiting reactant and get into our moles of what we're interested in finding out. So 2 coefficient for both. And so we will make 6 moles of water. And so as you can see, all 3 of these methods gave us the same answer. What's important is how we interpret our math, and to make sure that we're interpreting our math in a way that makes logical sense. All right, here is a practice problem for you. It reads, the reaction below is used to weld railroad tracks in remote areas because the reaction is so exothermic that the iron produced is liquid. What mass of iron would be formed if 113 grams of aluminum was mixed with 279 grams of iron oxide? Go ahead and pause the video and try to work that out on your own. Okay, you have an answer? Let's check. All right, so since this problem is asking for the mass of iron, then I'm going to be using the textbook method to solve this problem because that will lead me directly to my amount of iron. So I'm going to be, let's assume that all aluminum was used up. So if I use up all of my aluminum, then I need to figure out what mass of iron I could make from that amount of aluminum. So since I'm given a mass, I have to use the molar mass of aluminum in order to get to moles of aluminum. So that is 26.6 0.98 grams per mole. Next, I need to cancel out my moles of aluminum, and I need to get into moles of iron. That is a 2 coefficient and a 2 coefficient, so 2 and 2. And then I could end the problem there, or I can get into my mass of iron. And so I'm going to go ahead and do that. My moles of iron, so I'm going to use the molar mass of iron to find my grams of iron. So that's 55.85 grams per mole. Go ahead and calculate that. And so 113 divided by 26.98 times 2 divided by 2 times 55.85 is 233.915 grams of iron. And then I would only need 3 significant figures. I'll round after I figure out what is the limiting reactant. Okay, next I'm going to make a second assumption, and then I'll figure out which assumption was true. My second assumption is that all the iron oxide gets used up. And so I have to start with my aluminum oxide, cancel out my moles of iron oxide, and then I would get into, nope, not moles, grams. I need to cancel out my grams and get into moles. I need to get into moles of iron oxide. And so that's my molar mass. Let me calculate my molar mass. So I have 2 irons, 55.85 times 2 plus 3 times 15.999. That is 159.9697. All right, and now I need to use the coefficients from the equation. And so now I need to look at 1 versus 2. And so 2 moles of iron, 1 mole Fe2O3. Why did I make that too big? Fe2O3. Cancel out my moles of Fe. This is using my molar mass. And so the molar mass of iron was 55.85. Type that all into my calculator. 279. 59.697 times 2 times 55.85. And that is 195.146 grams. And I would need 3 significant figures. So what this math is telling us is that after using all of my iron oxide, I will make 195 grams of iron. I cannot continue on to make the rest, to use up the rest of my aluminum, because the reaction is going to stop after I make 195 grams. And so this is the most amount of iron that I can make. And so the answer to the problem would be 195 grams of iron. On this page, I'm going to try to solve the same problem, only doing the Alex method. So on Alex, what they'll have you do is figure out how much of the other reactant you would need. So if we refer back to the other page, it says that we start with 113 grams of aluminum, and we have 279 grams of iron oxide. So I'm going to be flipping back and forth between these two slides in order to grab numbers. But remember, we're comparing have versus need. have versus need. And then you ask yourself, do you have leftovers? And so I have 113 grams of aluminum. And I can use that to calculate, well, let's use my mass of iron oxide, which was 279. And so I have 279 grams of iron oxide. And then I have to calculate how much do I need. To calculate how much aluminum I need to, needed values are calculated. And so I have to use my 279 grams of iron oxide to calculate my how much I would need. So the molar mass of that was 159.17 grams, and so that's moles of iron oxide. Cancel out my moles of iron oxide. Get into moles of aluminum. And then from moles of aluminum, I would find my grams of aluminum, which is 26.98 grams. And then what were the coefficients? The coefficients were 2 and 1. 2 and 1. So 279 divided by 1, 59.697 times 2 times 26.98. That is 94.27 grams of aluminum. And then since this is calculated, that is the needed. And so I have to compare how much do I have versus how much do I need of the same compound. We always have to compare the same compound. And so I have 113 grams of aluminum, and I would need 94.27 grams of aluminum. And so that would give me 113 minus that number is 18.73-ish grams of aluminum left over. And now that I know that aluminum is left over, that is excess. And so my mass of iron would be solely dependent on this quantity of iron oxide. And so then I would do the same math I did before in order to solve the problem. I would take my mass of iron oxide, calculate my moles of iron oxide, calculate my moles of iron, because that's what the question asked for, find my grams of iron, and I would end up with the same number I did using the other method, which is 195.146,366, and I would still end up with 195 grams of iron made. Okay, so now let's assign some vocabulary. Yield tells us how much did we make. That's how much product did we make. In order to have a chemical reaction occur, you have to have reactant molecules collide into one another and to turn into products. Not all collisions result in a chemical reaction occurring. You have to collide, the reactant molecules have to collide and bump into each other in exactly the right way. And so if this bumps into there, then it might work, or it might just bounce off and, bounce off, or it could react, and then you might end up with some kind of fused thing happening. I don't know, but you have to have things bump into one another. All right, so they have to bump into one another. They have to have enough energy. You have to have them bump into one another. But the maximum amount of product you can make from the limiting reactant is called your theoretical yield. And so your theoretical yield is a prediction. It's a calculated value. So that's a prediction, calculated. And your actual yield is experimentally determined. That's how much you actually made. Your percent yield is a ratio of actual yield divided by theoretical yield. Your theoretical yield should be higher than your actual yield. Your percent yield should not be more than 100%. There's all sorts of reasons why your yield would be less than 100%. Some reactions just don't go to completion because the product molecules bump back into each other and reform reactants. Sometimes you spill, sometimes things land or you lose them on the side of your glassware. They get stuck in places they're not supposed to, and all sorts of reasons why your percent yield is less than 100%. You could even have side reactions happening that are not what you expected. So if you always know that your percent yield is around like 80%, then like you could figure out, kind of backwards calculate how much would you need to start with in order to obtain the amount that you desire. So in this example problem, it says this is the same problem we just solved, same masses from the previous limiting reactant problem, and we determined that we could make 195 grams of iron. And so now we've assigned a vocabulary term to that. We calculated that we could make 195 grams of iron. And so that is your theoretical yield. That's your theoretical yield. Now in the problem, we are told that the reaction produces 173 grams of iron. And so we're asked to find the percent yield, and we're told a mass amount. And so we're told this mass amount because that is our actual yield. So we do actual divided by theoretical, turn that into percentage, you end up with 88.7%. Okay, let's do this practice problem. It reads, without proper ventilation, the reaction of carbon and oxygen produces carbon monoxide. What is the percent yield if 40 grams of carbon monoxide is produced when 67 grams of carbon reacts with 30 grams of O2? Go ahead and pause the video and try to work it out. The balanced chemical equation is given on the right. Okay, you think you have an answer? Let's compare. This is your actual yield. We are told an amount of a product that was made in grams, and so that's our actual yield. we need to calculate our theoretical yield. We are given mass amounts of 2 different reactants. That means that this is a limiting reactant problem, and we have to figure out which reactant will run out first. And so I know that I have to cancel out my grams and get to moles. And then I will need to cancel out my moles and get into moles of the other substance, which in this case is carbon monoxide. And then I will use the molar mass of carbon monoxide to find my grams of carbon monoxide. Go ahead and plug in values. We use the molar mass. And the molar mass of carbon monoxide is 12.011 plus 15.999. It's 28.01. That's a 2-to-2 ratio, which is the same as 1-to-1. So 67 divided by 12.011 times 2 divided by 2 times 28.01. That would tell us 156.2 grams of carbon monoxide could be made. But I don't know if that's the theoretical yield or if O2 was my limiting reactant. So let's do the same type of calculation, only now with O2. So I can use my molar mass of O2, which is 31.998. Cancel out my moles of O2, get into moles of carbon monoxide. That is 28.01, same molar mass of carbon monoxide as above. And my coefficients are a 1 and a 2. Now we can type that into our calculator, and we get 30 divided by 31.998 times 2 times 28.01. That is 52.522 grams. Okay, so I can tell that the reaction is going to stop once it reaches 52.5 grams of carbon monoxide, because at that point all the O2 will run out. So this is my theoretical yield. So my percent yield is equal to actual divided by theoretical turned into a percentage. And so my actual yield was 40.0 My actual yield was 40.0 grams of carbon monoxide, and then my theoretical yield was that. Turn that into a percentage. And so that is 76.15%. 3 significant figures, 76.2%. Great.